let's look at the inverse function y equals sine inverse of x. So what's the derivative of this function? First, we must understand what inverses actually are. So why am I making a point about this? Because this is not sine to the negative first power, okay? I think students think this sometimes because it is standard that x to the negative first power is written as 1 over x. And why is this? The reason why is because if you look at the number 2, you multiply it by 1/2, that is the multiplicative inverse. It's multiplicative inverse because you multiply by it to get the identity. So you need to know what the identity is to know what the inverse is. Note that 2 plus negative 2, which is 0, is the additive identity. So there's not like an identity. 1 is the multiplicative identity, 0 is the additive identity, and the inverses give you the identity. So when it comes to functions, okay, what's the identity? It's actually x, okay? Why is it x? Because if you have the function, say, f of x equals sine of x, what do you put inside of this to get back the same thing? It's x, okay? If I put in like x squared, you get something different. But if you simply put in x, x is the identity because you get the same thing that you started with. Just like you multiply 2 by 1, you get 2, and if you add 0 to 2, you get 2. Okay, so back over here. So if this is the inverse, we don't actually have like as is really a way of doing this, but we can use implicit differentiation to derive the formula for this. Okay, so let's look at how to actually do this. All right, y equals sine inverse of x. What does that mean? What that means, I'm just gonna, draw this out a little bit. If you take the sine of both sides, because you have the sine of y equals the sine of the sine inverse of x, that's just x. So basically what this means is sine of y equals x. Okay, well, how does that help us? Because we know how to take that derivative, right? And we can use implicit differentiation. So the derivative of sine y is cosine y. And derivative of x is 1, okay? And so it's dy, should put that up there. Use the classic, you can just put y prime if you like. Use the classic Leibniz notation, so dy equals dx. And so what's dy dx? Dy dx equals, well, it's actually 1 over the cosine of y. Okay, so we're not quite there, right? And you might say, well, we've just gotten a little bit of a roundabout here. Like, how is this better? This is in terms of y, but what about having it in terms of x? Okay, well, we know that sine of y is x. So the idea is, let's actually convert this to the sine of y. And what we need here is our classic Pythagorean identity, which is the cosine squared x plus sine squared x equals 1. So we can rewrite this as dy dx equals 1 over, so you're just solving this, right? It's the square root of 1 minus sine squared x. So the square root of 1 minus sine squared y, because we have y here. But look at this, that's x. So what we have is 1 over the square root of 1 minus x squared. And we just used implicit differentiation to derive that the given y equals sine inverse of x, its derivative is 1 over root 1 minus x squared. Okay, I think personally this is tremendously cool. Nice little derivation. So in calculus, with some of the derivatives that aren't used as often, like sine inverse x, your choice is to memorize them or to know how to derive them, so that if you need to know it and you don't have an opportunity to look it up, that you can in fact get it. Now let's do a different one that's similar, just for practice. So this is a nice one. So how do we find the derivative of tangent inverse of x? Okay, so if you like, what's d dx tan inverse of x? Okay, what we can do is apply sort of the same technique. And so, okay, so if we start with y equals tan inverse x, and then we know what that means is the tangent of y, just like you're doing this to both sides, equals x. Sometimes I put the parentheses and sometimes I don't to speed it up a little. And then what do? Right? We can take the derivative here. And we can say that, okay, derivative of tangent is secant squared. So I get the secant squared y dy, we'll use the other notation if you like, y prime, equals, well in this case you just put the 1 up here, dx, and so we get y prime equals 1 over secant squared y. Now, how do you get the trig identity for this one? Okay, why do we want it? Because we want to get things in terms of x, and so if we get a tangent y there, we'll have like things in terms of x. So we've got that cosine squared of sine squared equals 1. So to put this in terms of tangent, what you can do is you can divide these each by, how do we get tangent? Tangent sine over cosine. Right, so if you divide everything by sine over cosine, sorry, that's what we want. Divide by cosine, you get 1 plus, just dividing by cosine. Sine over cosine is tangent squared, equals 1 over cosine is secant squared. Okay, so these are both Pythagorean identities, go together. And what we can do now is substitute in for secant of y, 1 plus tangent squared. And so we get y prime equals 1 over 1 plus tangent squared y. But note the tangent y is x, so we get the beautiful y prime equals 1 over 1 plus x squared. So this is particularly cool, I think. It's a very important derivative. The derivative of tangent inverse is 1 over 1 plus x squared. And it stands out because it's not, I mean, I guess this one's not another trig function too, but this one's a little bit cleaner and neater. It's 1 over 1 plus x squared. It's also very memorable. I will show in a future lecture, after you learn more techniques like integration, how we can use these in combination, and how Leibniz did to get the first derivation in human history of pi. Okay, we don't quite have the tools for that right now, although pretty close. So I do want to emphasize, just to wrap up the inverses, that there is an inverse of all the trig functions, and they have similar types of derivatives. No need to go over them all. You can either look them up or use this technique to derive them. I do want to mention, I guess, that if we look at like arc sine, you all seen this? So arc sine, just say arc sine of theta. Well, this is the same as the sine inverse of theta. Okay, it means the inverse. And sometimes people use the arc sine because it's it's not like ambiguous, whereas the negative first, it's like, how do we know that that doesn't mean to the negative first power? It's usually from context, I can tell you, but the derivatives are usually written like, what's the derivative of sine inverse in that format? Okay, so I do want to sort of go to something, I guess, related. What's left? What haven't we seen in terms of how to take a derivative? I mean, it's impossible to put absolutely everything up, okay? That's not the point. The point here is not to make an exhaustive list. It's to know how to do everything, know how to take every derivative. And you pretty much are there. But I do want to add, okay, so we know what the derivative of e to the x is, right? So derivative of e to the x is e to the x. So what's the derivative of something else? Any other number? Say like 2 to the x. So we've seen this, but we haven't done it in this video series, so it's good. Okay, so it's close to e to the x, right? So it should have like a, see, because it could be any number. It could be like 2.7. It's like, well, the closer you get to e, it's just going to be that number to x. And so it's going to have a 2 to the x here, okay? But it's got to have something else because it's not the identity. And that something else has to work for e to the x. So is there something that we could multiply by, that when we multiply it by e to the x, we would get 1, okay? So what can we do to e to get 1? And we also do it to 2 to get the right derivative. Well, the natural log of e is 1. So natural log of 2 is the correct answer. Similarly, if we want d dx of, we've done it of ln of x. What if we had log of another base, log 2 of x? What's this? Okay, well for ln x, it's 1 over x, right? So similarly, it's got to include like a 1 over x. But it's got to have something else there. And this is now just like the other one. It's going to be natural log of 2. So what I put up here for 2, this will definitely work for any base, okay, any number. So just want to add those couple derivatives. Now, what this does for us is it completes a portion of the course. And what this portion is, it's basically, we did introduction to derivatives with limits, which is its own part. And then we have, how do you take derivatives? That's a very significant part of calculus. We've looked at all kinds of different functions like sines, cosines, exponentials, logs, polynomials. We've also learned how to put them together, like with rational expressions using the quotient rule. We use the product rule, and we use the chain rule. We also use some rules implicitly, like the sum rule, which is just that you can take the derivative of e to the x plus, say, log of x as the sum of those two, because that's how limits work. And so at this point, if you know how to take the derivative of a particular function, which we've tried to cover all of them, you should be able to take the derivative of pretty much everything, okay? And with enough practice, you get good at it, I couldn't even stump you if I try, because the chain rule really is going to give you tons of mileage, and in combination with all these other things, it's one thing that students who take calculus get good at, which is taking derivatives. So what's going to come next then is a big second segment connected to derivatives, which are applications. And calculus has tons of applications. And so we're going to start to look at some of the applications, both within math and within science, that can give you a better sense of really why calculus is so powerful, and importantly, how to use calculus to solve some of the problems that you'll see.